Can the people online hear me now?
Yeah, perfect, thanks.
Oh, great, yeah, the first microphone must be broken. Okay, so all the people online have missed some introductory waffle and an explanation that if you want to download these codes, these notebooks, and play along, then please do, and they're at the link that somebody's just put in the chat. So this will be a very quick recap of the things that Michael covered and that Manon also covered in a little bit, just to establish my notation and set the scene a little bit. Yes, please.
Yeah, well, you can make it.
Maybe
you can add.
If I can get rid of that,
Yeah.
because that's going to be really annoying anyway, isn't it?
Yeah, that's better. Yeah.
That's probably as good as we can do. Okay, so I'm talking about n particles. Now, generally when we're simulating systems to explore their phase behavior, n might be hundreds or thousands. Here, n is going to be 7, okay, because we're working on our laptops and it's going to be nice and easy. I'm going to have a set of particle positions. This is an off-lattice model, just to be a bit different from the lattice things we've seen earlier in the week. So I've got a set of positions, Rj. The jth particle has a position vector r. I'm going to work in 2D, again, just to make things fast. And I've got some momenta p. And then I have a Hamiltonian, which is a potential energy plus a kinetic energy that is a function of potential energy being a function of the positions, kinetic energy being a function of the momenta. And I was absolutely terrified when I won't say terrified, when putting this together, I was worried, what if somebody asks me to justify the Boltzmann distribution? So thank you. I don't have to worry about doing that. So I'm just going to, again, take that for granted, as we all tend to do, that I'm looking to sample configurations. And by a configuration here, I mean a set of coordinates, Rj, that are distributed according to this Boltzmann distribution. So it's the magic e to the minus beta u, where u is this potential energy. I'm probably just going to call it the energy. I think Michael was calling it the potential. Physicists are terribly inconsistent in how we use language, so no apologies there, unfortunately. And then that's all normalized by the partition function z, which is just the integral over all of these configurations that are accessible of the Boltzmann factor. I'll work with inverse temperature. Beta is 1 over kT. K is 1 for all good theoretical physicists, so we don't need to worry about that. And as we've seen, we can't really evaluate this thing because it's high dimensional, and it's much more efficient to sample it with Monte Carlo than it is to do any kind of quadrature, even for 7 particles in 2 dimensions. I just wanted to briefly cover this idea of detailed balance that, again, we heard about yesterday. So I'm going to use the word microstate to refer to a configuration of the system. So a microstate will be the set of position and momentum coordinates. And if I think about a microstate A and a microstate B, then I'm looking for this detailed balance condition. Again, we've heard that this is a sufficient but unnecessary condition. I don't have to have detailed balance, I just need to have global balance, but detailed balance is much easier to enforce. And I know that if I have detailed balance, then I've got global balance. So we enforce this detailed balance condition. But the probability of being in microstate A times the probability of transitioning from state A to state B is the probability of being in state B times the probability of transitioning B to A. And then we construct our simple Monte Carlo algorithm by breaking up this transition probability into the probability of attempting a move and the probability of accepting that move in the usual way. And the way that we enforce detailed balance is we make sure that the probability of attempting a move from A to B is the same as the probability of attempting a move from B to A. And then we just have to worry about the acceptance probabilities. So we can satisfy that equation, provided those 2 attempt probabilities are equal with the Metropolis criterion, which is this thing here. So I make a move, being very careful to make sure that the probability of attempting the reverse move is the same, is the minimum of either e to the minus beta delta u, where delta u is the change in energy on making the move, or 1. Maybe one thing to stress that hasn't come up before is this is one choice. This is the Metropolis criteria. Quite a lot of physicists work with a different choice, the Glauber choice, which is a sort of sigmoid type function for the acceptance probability as a function of delta U. There's possibly other choices as well, I don't know. But everything we're going to do today will use Metropolis dynamics. I'm going to use that Metropolis criteria to decide whether or not to accept the moves. Probably historical ones that date back to 50 years before I was born. Michael may have a different view on that. I've lost him. There he is.
Instead of the minimum between between
okay,
the
so actually
regular.
that's something I was thinking about with because it's true that the part is not but our question in terms of dynamics, like for simulation and better property. It's like a PDNP, for instance, if you have some factorization variables, typically you're more advanced. But it allows you to then have some kind of better dynamics. Then you can do that. That's my take, but this is something that I was thinking about this year.
Okay.
You know, we had a story recently where a group started collaborating with us on kinetics of magnetization reversal in the Ising model, and all of our answers disagreed by a factor of 2. And we eventually realized that they were using Glauber and we were using Metropolis, and for some reason it's almost exactly a factor of 2 difference between the rate of magnetization reversal. The other reason I thought I'd just revisit this is to also mention a couple of common pitfalls. So quite often my first Monte Carlo code, people they remember this bit. Okay, that's my accept reject criteria, and they think, oh, I can make whatever move I like as long as that's my accept reject criteria, and they forget about the bit where these, in order to satisfy this equation, we have to satisfy this equation. And the way I'm doing that is making sure my attempt probabilities are anti-symmetric or are the same for the forward and reverse move, and then they end up with wrong results because they haven't obeyed detailed balance. They've just come up with some move and accepted or rejected it according to this probability. So I'll own up to one of these myself. Is we had a paper a number of years ago where we were simulating a polymer, so a collection of beads on a chain, and we had a move that lengthened the link between 2 adjacent beads, which is a move you can make. But the probability of the forward and reverse move, if you're just extending the bond, shrinking the bond, is not the same, because you have to account for the fact that when the bond is longer, there are more possible states you can start from, because there's a bigger surface area of the sphere that you can now live on, and you need to correct for that in the attempt probability. So we failed to do that in a paper and had to issue a correction 6 months later. There's also a very famous story about a liquid-liquid phase transition in supercooled water. So the idea is if you cool supercooled water or cool water below its freezing temperature, it becomes supercooled. And there's various people have careers invested in the fact that if you keep it liquid and you keep cooling it, there is a phase transition from one form of liquid water to another form of liquid water. And one particular model for liquid water, one group had a series of papers showing that this phase transition exists in that model. So let's call them West Coast. And then another group, East Coast, had a series of papers saying, no, that's nonsense, that doesn't exist. And the original paper was in Nature. There was a paper in Science by the other group. And then there were comments and responses to comments. There were shouty exchanges at conferences. These things almost came to blows at one point. The postdocs involved, by the way, the young people, they got on really well, and they wanted to sort this out. But it was only when one of the senior professors involved passed away that the postdoc was allowed to share his code with the other group. The 2 postdocs went, great, let's share codes, let's figure out what's going wrong. What was going wrong is the group that was disagreeing with the presence of this phase transition had made this mistake. So they were doing something a bit more complicated than this. They were doing a hybrid Monte Carlo type thing, but they weren't they had an accept-reject criteria that was incorrect. It assumed, well, it was just this, and it should have been modified to account for the fact that their moves they were making were not reversible in this sense. So that's a very increasingly famous example of very high-profile papers being debunked by getting this wrong. So even the best people at groups are making mistakes. Incidentally, the paper that was published jointly by the two groups after the professor's death, where they explained what they'd done wrong, is they said, for an explanation of why this is incorrect, see this paper by David Quigley and Mike Allen. And I was like, brilliant. I was very pleased with that, because I didn't write a single line of that paper. Okay, so just again to a bit more broader context, other ways that I can satisfy this equation is I can bias my choice of move. We've heard a bit of that in the context of cluster moves is one way of doing that. There's this whole spectrum of methods that mix molecular dynamics in Monte Carlo in some way, which at one end would be what I would call force-biased Monte Carlo. So I would keep the momentum degrees of freedom, and I would evolve them doing, but I wouldn't evolve them doing, sorry, I wouldn't keep the momentum degrees of freedom, but I would use the fact that I can compute a gradient of my potential energy, and I would bias my direction of single particle moves to be more probably selected along the direction of that gradient. And then I would adjust my acceptance probability so that I maintain detailed balance. So I would call that force-biased Monte Carlo. And then at the other end of that spectrum, you've got the hybrid Monte Carlo things that we heard about yesterday, where you just evolve some Hamiltonian dynamics and then accept or reject that. I also wanted to mention, I'll come back to that later when I talk about a pathology. The other thing I should just briefly make clear before I set off, and somebody asks what happened to K and P, is if it's not obvious to this audience, all of the distributions that I'm interested in, all of the quantities that I'm interested in, the contribution that the momentum degrees of freedom make, provided I'm at equilibrium, I can compute analytically. I don't need to do any Monte Carlo. So it's just a Gaussian e to the minus p squared over 2m in each degree of freedom. That's separable. We can all integrate a Gaussian. And so we don't need to do any Monte Carlo to evaluate that bit. So everything's just going to be in terms of positions and potential energy U. Okay, so my model that I'm going to simulate, and it's very simple. I've got an atom. It's attached with not quite a spring. It's a non-linear spring to its friend, and then its friend is attached to its friend with a spring. So on. I'll stop drawing the springs, and I've got 1, 2, 3, 4, 5, 6, 7 of these guys, all connected with springs. So a spring means that I've got some energy function as a function of the separation between two adjacent particles on the chain. That energy function has a minimum at some bond distance, some preferred distance apart for the adjacent atoms on the chain. If I stretch that bond, the energy goes up. If I compress that bond, the energy goes up. Okay, so it likes to sit at a particular distance. And then for anything that is not directly bonded to a neighbor, so say the interaction between this guy I and this guy J, I'm going to use a standard Leonard-Jones interaction. If you don't know what a Leonard-Jones interaction is, it's a pair potential. So as a function of the distance between I and J, I've got this contribution to the energy phi that I add up over all the pairs that aren't directly bonded to each other. And again, there's a preferred distance apart so that beads that are not directly bonded to each other want to sit, which is going to be set to be about the same as the bonded distance. So the non-bonded minimum energy distance is the same as the bonded minimum energy distance. If I try and push them closer together than that, again, I'm talking about non-bonded pairs, energy goes up very quickly, so these spheres can't overlap. And then there's an attraction at long range, so the gradient of this is such that up to any distance out to infinity, basically, it's attractive until it reaches this minimum. So that's my simple model. I'm not going to bother with periodic boundary conditions because I've just got a chain of atoms tied together. Sorry?
the connections that are not the springs.
For the ones that are springs, it's a nonlinear spring force, which I haven't plotted. The connections that aren't springs.
No, yeah, the one.
Oh, that's just I got bored of drawing springs. Sorry, they are all springs. Yeah, yeah. That's just me being lazy. Sorry. Okay, so I'm going to import my standard Python things. These are just plotting functions that are going to let us visualize what's going on. I'm working in 2 dimensions with 7 beads, and I've written myself this little Python class that computes these energies and computes for efficiency. It's quite important to be able to compute how the energy changes when I only move a single bead. I don't want to recompute the entire energy of the system if I've only changed 2 degrees of freedom, i.e. the position of one bead. So there's a function in there that will compute what is the energy or is the contribution to the energy that involves a particular bead. Oh dear, right, that was bound to happen, wasn't it? Polymer object has no attribute R. Oh, I know what I've done there. It is underscore R, yes. At the last minute, I thought I'll do proper Python, and I'll put an underscore in front of things that are meant to be private to the class. So where am I using underscore R? Draw chains? Oh, yes, there we go. Thank you very much. So I just need to redefine that. That's the only time we're going to use that function, so fingers crossed it's not going to go wrong. So I've started off with this thing in a very boring configuration. The fixed bead is at the origin, and the others are just in a line separated by the equilibrium bond distance.
And here the state space is